My name is Jingmai O'Connor, and I'm the Associate Curator of Fossil Reptiles here at the Field Museum. So the study of living birds is ornithology. So I am a paleoornithologist. I don't usually use that term. I just usually say I'm a vertebrate paleontologist. But my speciality of research is the early evolution of birds. So birds that live in the Mesozoic, which is about 252 to 66 million years ago. I'm from California, Southern California. I grew up in Pasadena, home of the Rose Bowl. And I went to Occidental College. Just randomly based on the financial package they gave me. But I'm actually really glad I went there because I had no inkling that I would ever be a paleontologist. I had no interest in paleontology until I went there and I met a paleontologist working there named Don Prothero. He was just such a great teacher that he sparked my interest in evolution. I was already a geology major because my mom's also a geologist. We actually did our PhDs at the same place 12, 13 years apart, actually. And so I was following my mom's footsteps to be a geologist, but didn't really know what area of geology I wanted to pursue. I hadn't really found my passion yet. And I was just kind of, I'm going to be a geologist like my mom because my mom's the coolest person ever kind of thing. And and then I took this class called historical geology, which basically goes from the Big Bang to modern day. It takes you from how the universe forms, galaxies, solar systems, planets, all right, then they focus on Earth and it takes you right up to modern day. So part of that is the appearance of life on our planet and how it's changed, in the past 1.8 billion years at least, right? And I just got hooked on the concept of evolution. And if you are going to study evolution as a geologist, you do that as a paleontologist. You do that by studying fossils. It's not the only way to study evolution, of course, but you can be a biologist who's messing around with fruit flies, but I much prefer the paleontology route. But yeah, that's a little unique. Most paleontologists have known that this is what they want to do since they were yay high or since they saw Jurassic Park or whatever. But it's really 99% of them is one of the two. And I'm not there's nothing wrong with that. But yeah, so if I hadn't gone to Oxy, I wouldn't have discovered paleo and I wouldn't be here. So I'm very, very grateful for that financial decision that I made. I made a practical choice to work on birds because I thought, well, I've been told that paleontology is super competitive and that, only the strong survive. No, I'm just kidding. But they say 1 in 100 paleontology students actually makes it. So it is super competitive. And so I thought, well, if I'm going to do this very competitive, pursue this very competitive career, let me at least give myself let me give myself a fighting chance. And at this time, it was when all these early Cretaceous birds from China were just pouring out of northeastern China. And so I thought, well, I'll work on birds because this is an area where there's going to be an enormous amount of growth. So this means that if I'm part of that, I'll be able to make an impact in the field of paleontology. I really honestly think that no matter what organism I chose to dedicate my life to, organismal group, I would have fallen in love. If they were nematodes, I'd be wearing a nematode shirt right now. I think because all organisms are fascinating. People talk about, oh, charismatic megafauna and things like that. And I don't buy into that. I really think that all organisms are super fascinating. You just have to really focus your attention on them and ask why. And then everything is weird, everything is fascinating. At first there was actually a period of time where people are being a bird paleontologist is the worst because nobody wants a bird paleontologist. They want mammals or they want dinosaurs, and when you tell them birds are dinosaurs, they're yeah, but not really. We want a dinosaurs. And I was really actually feeling that until I got this job. And I was oh, cool. I guess people do want bird paleontologists. So I'm, really grateful to be here. And, it's just a dream come true. I still sometimes can't believe that I'm here and that, that I, have such a wonderful position. I started the job in October 2020, but in March 2020, the Field Museum reached out and they said, we're in the middle of this really big acquisition, and we don't have a curator who can provide scientific consultation on this acquisition or for this acquisition. So they sent me an NDA, and then I got to help move this deal forward even before I began the job. So the Chicago Archaeopteryx is the 13th skeletal specimen that has ever been found in 172 years of discovery. So if you had asked me, is this a dream come true, I would have told you I never would have ever thought to dream that I would get an Archaeopteryx to work on. And so then, this deal being brought to my attention, I was like, oh my goodness, like, how exciting. And then this emotional roller coaster, are we gonna get it? Are we not? That was crazy. And then the specimen finally arrives. And the thing is, the specimen was unprepared. So all we could see of the specimen were the arms, but with the feathers attached. So with an Archaeopteryx, the wings are the most important part, right? Archaeopteryx, ancient wing. That's really, if you're gonna have an Archaeopteryx, having the wings there means that you already have the most important part. We also had, in a little side slab, a foot. So we had reason to hope that kind of everything in between might also be there, but we really didn't know. And, so it was really stressful for me because I'm encouraging the museum to make this acquisition, but, people are like, is it gonna be worth it? And I'm like, I don't know. Like, yeah, it was so stressful, so much pressure. And so the specimen finally arrives in the Field Museum, and we, unpack it, and it came in this like sarcophagus that looks like something from Indiana Jones, like a box within a box, like built specially for the specimen. So we're unscrewing it, we're opening layer after layer, and once we get the specimen out, we take it right away over to this X-ray machine that we have here in geology. And everybody's crowding into this tiny little room, and we have our GoPros or our camcorders. We're recording this whole thing because this is a important historical moment for the Field Museum. And Bill Simpson, the head of geology collections, and we put it on the X-ray bed, and then we all kind of exit the room, and we're all staring at the computer screen that's going to show us this image. And when the image showed up, and you could see just the complete specimen in the classic death pose with the head back and the wings out, just like the Berlin specimen. I mean, it was this, this moment where everyone in the room was like, whoa, we all clap our hands. We were so excited. Boom, there it was, the complete thing. And it was, so exciting, but also I'm going to say an enormous relief, because if I had, encouraged the museum to acquire the specimen and then it turns out all we had were the wings and a foot, I would have been like, well, it's still cool, but now I can be like, this is super, super cool. Birds do not appear to about 150 million years ago, and the very first one that is 150 million years old is Archaeopteryx. Archaeopteryx is also the first Mesozoic bird that was ever found. So when it was collected in 1861, that was the only Mesozoic bird that was known. And even now, 164 years later, it is still the oldest Mesozoic bird that's ever been found. It is the only bird known from the Jurassic. So Jurassic bird, very cool. When Darwin published On the Origin of Species in 1859, the idea that organisms change through time was already known, but the mechanism for that change was what Darwin provided, right? Natural selection. And so, he writes this book, which was an instant bestseller, actually. It was surprising, and he lays out his theory of evolution by means of natural selection. But, and because of, his theory, he says, well, we should find these transitional organisms that record one lineage evolving or diversifying and branching off into other lineages, right? So you should find these transitional forms that will, for example, record the transition from a very reptilian-looking reptile, scaly, cold-blooded, long tail, to a bird reptile. There should be some, in the fossil record, there should be animals that record that transition, the changes that didn't instantaneously appear, that evolved through time, through natural selection, right? But he points out in his first edition of the book, he says, if for all those people who are going to disagree with me, the biggest argument against my theory is that as yet we have no such examples in the fossil record. We know of no such examples. We have no transitional forms or missing links that we can point to and go, boom, right there, that's why I'm right. So, but he also, you know, being a smart guy that he said, well, this is because right now the fossil record is extremely incomplete. Like at that time they knew of like what, 3 or 4 different species of dinosaurs. I mean, there just not a lot of work had been done, not a lot of fossils had been dug up, so they didn't have a lot of material to work with, right? 2 years later, the first Archaeopteryx is found. And there's actually this really good letter. I wish I could quote it from memory, but it's a letter from like a friend writing to Darwin. And he's like, you know, if you had to make up something to like prove yourself right, basically, you know, you couldn't have done better than the Archaeopteryx. He wasn't trying to allude that like you made that up, that's a fake fossil. He was just saying like, if you needed something to prove you right, like, you know, like you couldn't have, like, there was nothing that could have been better than an Archaeopteryx because it has wings, and at this time, the only animals we knew of that had feathers were birds. And not only does this have feathers, it has feathers forming wings that look fairly, like pretty close to a modern bird's wing. But then the skeleton, there's almost nothing bird-like about it. It is so important, both scientifically and historically, I think. You know, we are so lucky to be the first major natural history museum outside of Europe to have one of these specimens in our collection. The Berlin Museum guy, you know, the head of the Berlin Museum was like, yeah, like we keep ours like under Fort Knox, you know, and if you go to the London Natural History Museum, they have one small room which is kind of like supposed to be like their most precious treasures, you know, and the London Archaeopteryx is in that room. You know, and Archaeopteryx, you have no sternum and you have 3 claws on the hand like you have in most non-avian, and like you have in theropod dinosaurs closely related to birds. You have the long bony tail. And then, you know, as you look to the next oldest birds, these birds from China, you start to see them lose the claws on their fingers one by one. You start to see the ossified sternum appearing, and you see the sternum get bigger and bigger and the ventral keel appear. And so the sternum is critical for birds because that's where the flight muscle is attached. So when you're eating the like when you eat a chicken breast, it's a pectoralis muscle, and it's responsible for the downward stroke of the avian powered flight, which is where all the work occurs. And then there's just like a little pulley-like tendon that goes whoop and pulls it back up, and you have this big muscle then again pushed down. So, you know, this is something that, you know, it's a really fun experiment for little kids to put like wings on them, like big, thick, you know, like aerofoils, and have them push down and see how much the air resists you. You need big muscles for that. And in some birds, these flight muscles account for almost 30%, like, you know, for almost 1/3 of the entire mass of the animal. So it's such a big muscle. So you need to have a big bone for it to attach to, and this bone is the sternum. And Archaeopteryx has no bony sternum. It's one of the biggest mysteries about this bird. Like, where did the pectoralis go? How did it fly? Something we still don't know. Something that I do hope to test with our CT model in the future, but you know, for a later date. But anyways, you can trace, you know, in these birds, these Cretaceous birds from China, you can see the acquisition of more and more bird-like features until you basically get taxa that look just like modern birds, but still retain teeth that are from the late Cretaceous, birds like Ichthyornis. And then we also even do have very, very rarely from the latest Cretaceous fossil members of the group of birds that are alive today, which we call Neornithes. You did ask one question about, is Archaeopteryx, like, did all birds evolve from Archaeopteryx? Yes. And I would like to address that, because even though Archaeopteryx is the oldest bird, it is not the one single common ancestor of all birds. So all organisms share a common ancestor, and for all more and more exclusive groups, there is a common ancestor for that group, a single hypothetical common ancestor that we will never know because of the nature of the fossil record. But we know from the morphology, from the shape of Archaeopteryx, from the shape of its body, that it is not that hypothetical common ancestor taxon. It is its own offshoot from that taxon, and it has its own unique evolutionary history that is unique to the Archaeopterygidae lineage that died out and probably didn't survive past the Jurassic. So yeah, so it is not the common ancestor of all birds. That's something we'll never know, but it is the oldest bird, and it is the most primitive bird. So evolutionary biologists don't like the word primitive, but the word basil is not really understandable to most people. But so, for lack of a better way to say it, it is the most primitive bird that we know of. And it is the closest, that proxy we have for understanding what that earliest bird would have looked like. The thing is, when you tell people birds are dinosaurs, when they think of dinosaurs, they think of Stegosaurus or Triceratops, and then they think of a bird, and they're not similar at all. But we have to remember that, you know, the Dinosauria was this enormously diverse group that was successful for a very long period of time. And so if you look at dinosaurs that are more closely related to birds, then you start to see the similarities. You know, so for example, even once you move to T-Rex, then you start to see that its legs look very much like a chicken, right? And then when you move even closer within the Theropoda, which is the group of dinosaurs that includes T-Rex, Archaeopteryx, living birds, like they're all theropod dinosaurs. And so if you get even closer to birds within Theropoda, you look at, say, a dromaeosaurid like Velociraptor, then you're going to be like, oh, all right, this Velociraptor is a dinosaur, birds are dinosaurs. You really see so many like similarities in terms of the skeleton, but also the integument. That's the soft tissue that's covering the body. Because Velociraptor would have been covered in feathers, just like a bird. It would have had small wing-like structures on its arms, even though it wasn't flying, and you know, would have had the same scales on its feet. Actually, the scales on the top of the feet have secondarily evolved from feathers, which is interesting. So like the ones on the top of the foot overlap and the ones on the bottom don't, because the ones on top were feathers and then evolved back into scales. Anyways, they would have had a lot of very similar features that I think then make it a lot easier for people to understand that birds are dinosaurs. So actually, like scientists now, if you say birds and you say dinosaurs, that's not correct. So we actually say non-avian dinosaurs. It's very cumbersome, so usually what we'll do in a paper is right off in the paper we say, when we say dinosaurs, we are referring to non-avian dinosaurs. Because if you're trying to separate birds from dinosaurs, that's incorrect. Like, birds are dinosaurs, so you can't talk about them as a separate group unless you specify non-avian dinosaurs for all the other dinosaurs. The idea that birds are living dinosaurs didn't really become widely, if not universally, accepted until the discovery of feathered dinosaurs from China in the late 1990s. Because when you see, like, you know, at that time, feathers are something that are so uniquely avian, right? And then you see these fossils from China, spectacularly well preserved, with feathers forming little proto-wing-like structures on the forelimbs. That is evidence that anyone, even if you're not a trained paleontologist, can look at and draw the connection between these dinosaurs and birds. And actually, the same decade, at the end of the decade, in 1999, the first nesting dinosaur was described. And so it's a dinosaur that also would have had modern bird-like feathers. It's an oviraptorosaur. Its name is Siddipati, but anyways, it also would have had an edentulous rostrum. It would have had a beak like birds, and it was preserved sitting on its nest with its arms, which would have had little wings, preserved stretched out over its ring of eggs. And actually, at that time, we didn't know, is it just protecting its eggs? Did it die laying eggs? And it actually wouldn't have been brooding them. It wouldn't have been contact incubating them with its own body heat the way living birds do. Like, that was very controversial at that time. But within the past couple years, there's been more brooding oviraptor dinosaurs that have been found that do strongly suggest that these dinosaurs were also contact incubating the same way living birds do. So again, this is tangible evidence that anybody can see. They can look at and see this very avian characteristic. I mean, no other reptiles, you know, brood their eggs like this, and you can see it in dinosaurs, and then you can really draw the connection. And the last fossil, it's my absolute favorite. It's a little troodontid dinosaur, so very closely related to Anchiornis up there, and it's called Meilong, which means sleeping dragon, and it died in its sleep. It died probably in a pyroclastic flow, so like, you know, it's like basically a cloud of ash that kind of moves like a liquid that's from a volcano, and it was just instantaneously killed, so you don't have to feel bad for it. But it's preserved sleeping with its tail wrapped all the way around its body, Okay, birds don't have tails, so ignore that part. It's just cute. But it's preserved with its head tucked under its wing. And if you think about, like, you know, everyone has seen ducks sleeping, right? And or like a goose or a swan, and how they tuck their head under their wing when they sleep. All birds do this, with the exception of like penguins and like birds that aren't unable to do it. But yeah, again, this is tangible evidence, that undeniable evidence that you don't have to be a paleontologist to understand. And I think that's actually really important for people to, you know, to move beyond just like the scientists arguing about the morphology of the semi-lunate carpal or whatever, to really something that everybody can understand, and kind of bring us, like, as a civilization to understand and accept this knowledge. So the research on the specimen, which was, of course, the best part, at least for me, you know, I banged out 3 manuscripts, which I sent to Nature. Banged them out in less than 3 months. So that was crazy. Patch of gray hairs. Thank you. Anyways, but yeah, you know, this is just the beginning. We CT scanned the specimen, and so that is just, you know, a treasure trove of data that we can use for so many things, like biomechanical studies on all aspects of the skeleton. Of course, the most important is the wings, you know, kind of really testing this hypothesis that it could fly, and then really going, investigating how it flew. That's the most important biomechanical project that we have planned, but also looking at even just things like the reversed first toe and how that function. And I mean, there's just tons that we can do there. And beyond that model, I have a million projects in my mind that I want to do, looking at the bone tissue, how this thing grew, you know, like further like geochemical analyses to really understand where this bird fit in the food chain. I mean, I could go on and on. There's a lot we can do, and I'm not going to do it all by myself. I have a diverse and international group of collaborators that I'm working with, because, you know, every scientist has their own little speciality. So yeah, with this wonderful team, and also with the other researchers who reach out to us with their project ideas, we're going to learn so much from this specimen. Can help us understand what set that one group of birds apart from the other groups of birds, as well as their non-avian dinosaur relatives, and that can help us understand what permits organisms to survive through periods of extreme environmental crisis. Paleontology in like past decades has really been seen as like kind of a gateway science. Like paleontology gets people excited and starts thinking scientifically, and then maybe they'll segue into a more useful scientific career. Like that's kind of been the thinking. And so, you know, of the dinosaurs that attract people, get people excited, T-Rex, you know, is the winner hands down, right? I mean, and T-Rex is a really awesome animal. But as I always like to point out, it is an evolutionary dead end. But it's also only recently that paleontology has become relevant in itself as a discipline, because now we are in the 6th mass extinction in Earth's history, caused by us, yay. But this is we are a planet in crisis. We are a civilization in crisis. And we desperately need information to guide us through this crisis. And the only way for us to understand how organisms respond to climate change, to you know, massive, you know, environmental changes, how different lineages of organisms respond to mass extinction, that we can only study this through paleontology. So now paleontology has gone from something that is like fun for kids, get them into science, to something that is absolutely relevant to the most pressing concern that humanity is facing at this moment. And if you think about the most recent mass extinction, besides the one we're in, is the 5th mass extinction that is most famous for wiping out non-avian dinosaurs, but one group of dinosaurs survives, birds. So actually studying why this one group of dinosaurs, or this one subset of this one group of dinosaurs, survives is actually very relevant to the current environmental crisis that we're in. I really haven't had time to sit with it and just revel in the glory of the specimen, except this one moment. So we were given a like staff wellness day, like nobody come to work this Thursday. You all have this Thursday off. Nobody come in. And actually I had to ask permission to be allowed in the building so that I could spend that one day when the preparators were not going to be working on it, studying the specimen. So this was when prep wasn't quite finished, but it was almost finished. And so that day, yeah, I came in, the museum's empty, it's just me and the Archaeopteryx, and Yeah, like I got emotional, you know, like I almost cried. I mean, at that point, I was just working on the skull. Initially, I was just going to write one first paper just on the skull because that was what got prepared first, and it's the like hands down, without a doubt, we have the best Archaeopteryx skull of them all. I mean, in terms of like which is it the best specimen of them all, I feel like that's you know, that's more subjective. I definitely think we have top 3 in terms of overall specimens, but the skull, definitely the best. It's beautiful. And yeah, just, you know, I spent several hours, like, I mean, I would have spent longer, but honestly, staring through a microscope for a really long period of time, like, it gives you a headache. So yeah, I spent about 3 or 4 hours just, you know, studying the specimen, taking notes, working on the line drawing, and just, yeah, really getting emotional and really finally having that moment to be like, oh my goodness, like, look at this beautiful specimen and how lucky am I that I get to work on this incredible, incredible fossil. But yeah, I'm looking forward to, I think, when all the craziness has passed and I can, again, you know, you'll probably find me hanging around the exhibit just like gazing at it adoringly. I'm just kidding.